Now, one of the most common ions to be used in this common ion effect are hydronium and hydroxide. So consider magnesium hydroxide. Now, this is a salt that is not soluble much at all. In fact, but the presence of, in some cases, hydronium or hydroxide can greatly affect its solubility. Now, in pure water, the KSP for this thing is 1 times 10 to the negative 11. So note, small. So which means that the magnesium concentration times the hydroxide concentration squared will be 1.8 times 10 to the 11th. So let's consider the solubility of magnesium hydroxide in a weak acid solution. So that's about 1 times 10 to the negative 3. So that is about, not about, that is pH of 3. Now remember, the concentrations of hydronium and hydroxide are related by the water autoionization equilibrium, which means that under those conditions the hydroxide concentration is 1 times 10 to the negative 11 molar. So what would the magnesium concentration be if the hydroxide concentration was actually kept at 1 times 10 to the negative 11 molar? So let's say that this solution was actually buffered to stay at pH 3. Well, you would get this setup right here. And that would, so if you solve for the magnesium concentration, you should find that it gets very large because you are dividing by this very small number twice. And if you work it out, the equilibrium magnesium concentration is 1.8 times 10 to the 11 molar. This is an insanely high concentration. You never actually achieve that. So the way that most people describe this is they say that the solubility of magnesium hydroxide is much higher than it is in acid solution. I'm not a fan of saying it that way because in this case, it's not the hydroxide, it's not that this thing is dissolving. What happens is that in this acid solution, as soon as the hydroxide is dissociated, it's reacted away, which means, and then so think about this in terms of Le Chatelier's principle, right? So you are continually removing one of the products, which means you're just going to keep on making it. So this reaction just is continually shifted to the right until the acid is depleted. So this is why these hydroxide salts, which are generally most of them are not soluble in water, but they are quite soluble in acid because they react with it. So let's talk about another example. Barium fluoride, for example. Barium fluoride is not particularly soluble in water. In fact, it is used as a window material for things that, there are some cases where you need a window material to be made out of an ionic compound, but a lot of them, dissolve in water, so they're not appropriate for wet examples. And barium fluoride is not one of those because it's not particularly water soluble. So here is the dissociation process. Barium fluoride splits up into an aqueous barium and 2 fluoride ions. But now, would this be more acidic, more soluble in acidic solution than it is in pure water? And the answer is, yeah, it would be, because the fluoride is a base. So as soon as this thing, if this is in an acidic solution, as soon as, the first, minuscule amount of fluoride is dissociated, it is instantly reacted with the hydronium ion to make HF, and this equilibrium is again continually shifted to the right until something runs out, until the acid runs out or something along those lines. And that, again, that's because this reaction, because it's the reaction of a strong acid and a weak base, essentially goes to completion. And so that continual depletion of the fluoride it's going to cause the barium fluoride to be continually dissociated, which will result in a higher than you would expect barium ion concentration, just like it did for the magnesium. Now, home stretch here. Precipitation is the opposite of solubility. So let's look at our barium fluoride system again here. So the KSP for this is the barium concentration times the fluoride concentration squared. And in this case, it happens to be equal to 1 times 10 to the negative 6. Now, think back to the original equilibrium chapter. We learned about these things called reaction quotients, of which equilibrium constants are merely a subset, but they're constructed the same way, except that you're putting in concentrations that are not necessarily equilibrium concentrations and that are probably not equilibrium concentrations. And so the idea is that if the reaction quotient is larger than KSP, that means that these concentrations are higher than the equilibrium concentrations can be, which means you will form more of the solid, you will precipitate to reduce those concentrations, and that process will continue until the concentrations give you the equilibrium constant number. If they happen to be equal to KSP, then the system is at equilibrium and you've got no net change. And if Q ends up being less than KSP, that means these concentrations are lower than they are for an equilibrium mixture, which means it will continue to dissolve until Q equals K. And so this is how one can predict, if given a certain set of concentrations, they will remain in solution, if they're at equilibrium, or if the concentrations will drop as a result of precipitation. And that, folks, is the end of the equilibrium chapters. You may cheer, clap, do whatever. We're not done with equilibrium, but we're done with it being the main topic of a chapter, and we will now move on to something fairly different, but related. All right, see you next time.